Many people assume comets are rare, once-in-a-lifetime spectacles. So when NASA says 7 are diving in at once, concern and curiosity spike immediately. The problem is separating what could alarm headlines from what actually matters scientifically. The solution is to unpack what NASA is truly alerting about: observational opportunities, interstellar comparisons, and what we may soon learn about the origin of comets themselves. By the end, you'll know why this event is interesting, not alarming. 7 visitors at once. Most people picture comets as solitary wanderers, a streak across the sky once every few years, occasionally bright enough to draw headlines, then gone again for decades. Right now, though, astronomers are tracking 7 inbound comets at the same time. That is unusual. Typically, only 1 or 2 large enough to study in detail make their way into the inner solar system within a short span. But this cluster means researchers suddenly have a small crowd of icy bodies to observe. In plain terms, a comet is a frozen mixture of water ice, rock, and dust. These fragments likely formed very early in solar system history, preserved in cold regions far from the sun. As they travel inward and sunlight heats their surfaces, the ices turn directly into gas. This gas pushes dust outward, creating the glowing, fan-shaped tail many people associate with comets. Even though popular culture presents them as dangerous omens, comets are really fragile time capsules holding material almost unchanged for billions of years. To the casual observer, seeing 1 comet pass in a lifetime may seem like a rare event. That perspective makes news of 7 at once feel startling. Instead of 1 solitary spectacle, an entire group is arriving, each carrying information about its origin. Among them is 3I Atlas, which gained attention for following a path not bound to the sun. The eye indicates interstellar, showing it came from beyond our solar system altogether. Now, this unusual traveler appears less lonely, accompanied by other comets that do orbit the sun on repeat cycles. The difference matters. Interstellar comets, like 3I Atlas, carry material shaped in another star system, while solar system comets formed close to home, in reservoirs such as the Kuiper belt or the Oort cloud. Observing both kinds side by side allows scientists to compare their makeups. It is a chance to see whether distant planetary systems create bodies with the same ingredients we find near Earth. That makes this gathering less about threat and more about comparison. One way to picture this sudden clustering is to think of migratory birds. Usually they pass overhead a few at a time, but occasionally an entire flock appears, moving together before scattering again. The appearance feels unusual, but there is no reason for alarm. Likewise, 7 comets arriving within close observational range is irregular, but naturally possible. Each of these objects has its own orbit and its own chemistry. Some release more carbon-rich gases, others show stronger water vapor emissions. Because they behave differently near the sun, studying them side by side builds a clearer picture of comet diversity. That said, not all may survive the journey inward. Some could fragment when stressed by increasing heat and tidal forces. This outcome is uncertain and depends on each comet's size, shape, and the strength of its internal structure. So, when NASA issues an alert in this case, it refers to a unique chance to measure, not a warning of immediate danger. The real question is what happens when those 7 icy visitors swing close to the sun, and how spectacular their transformations might appear once they reach that point. Close approaches to the sun. When people hear a phrase like diving comet, the first thought is often about collision. Could one of these icy bodies crash into Earth? The consensus view is no. None of the 7 inbound comets has a predicted path that comes close to our planet. Their real drama unfolds much nearer to the sun, not here at Earth's orbit. What matters most is a point astronomers call perihelion, which is simply the closest approach of a comet to the sun. Each of these objects will reach a perihelion distance that is close enough to trigger change, yet still millions of kilometers away from us. At perihelion, a comet experiences extreme conditions. The sun's gravity pulls at its structure, while the heat drives rapid transformation. A process called sublimation begins, where frozen ices vaporize directly into gas without melting first. This escaping gas carries dust along with it, spreading outward into space. The familiar bright tail we see in photographs is sunlight reflecting off those dust grains and gas molecules. It is a natural reaction to solar heating, but it places great stress on the body of the comet itself. Some comets endure this stage fairly well. They shed material but keep their cores intact, allowing them to swing back into the outer solar system and return again centuries later. Others can be overwhelmed. Sun-grazing comets, which pass extremely close, sometimes disintegrate entirely. A notable example was Comet Lovejoy in 2011. It brightened spectacularly as it skimmed the sun's outer atmosphere, but then broke apart soon after. That event highlighted how fragile these icy bodies can be when they face the sun head-on. What happens to the upcoming group is still uncertain. A working hypothesis is that some will fragment into multiple pieces. If that occurs, each fragment may develop its own smaller tails, giving astronomers several objects to track instead of one. Fragmentation often explains sudden outbursts in brightness seen in ground-based telescopes. When fresh ice is exposed after a breakup, the sunlight can cause a brief surge in activity before the pieces fade again. The phrase "close pass" can be misleading in astronomy. Even when astronomers say a comet comes very near the sun, the distances are enormous by daily standards. For comparison, Mercury orbits at around 58 million kilometers from the sun. Many comets come no closer than that, and Earth remains tens of millions of kilometers farther out. So, while the path brings them into a bright show near the sun, the geometry keeps them very far from us. For observers on Earth, the main effect could be temporary increases in visibility. If one of the comets develops an especially active tail or survives perihelion intact, it might brighten enough to be seen in binoculars or even faintly by the naked eye. These would not be threats, but rather brief natural displays. The real concern remains the comet's own survival. And while that question plays out, NASA continues refining orbits in the background to ensure trajectories pose no risk at all. This monitoring leads naturally into how the agency keeps track of possible hazards overall and why alerts are issued in the first place. Watching for danger. The word alert can sound alarming when attached to comets, so it is natural to wonder if NASA's language means danger for Earth. In reality, alerts come from a part of NASA designed to increase vigilance and information sharing. That office is called the Planetary Defense Coordination Office. Its task is not to produce alarm, but to organize the search for objects that move close to Earth's orbit and to coordinate how new data is shared across observatories around the world. Alerts signal activity in the sky worth monitoring, not an emergency. One important distinction is that the office was created to focus on near-Earth asteroids, because those are rocky and more likely to survive entry through our atmosphere. Asteroids can pose potential impact hazards over long timelines. Comets, however, are largely different in character. They travel at higher speeds and have more elongated orbits that stretch deep into outer space. Because comets tend to fragment when heating up near the sun, the chance of them reaching Earth intact on a threatening trajectory is very small. For the current 7 comets, all of their orbits keep them millions of kilometers from us. Still, scientists take nothing for granted. When a new object is discovered, the first step is measuring its position carefully night after night. This is how orbital predictions are built. At first, the orbit can only be estimated, but as more measurements come in from separate telescopes, the uncertainties shrink. This process is very similar to plotting the track of a storm. At first, you get a broad cone of possible paths. Then, as observations accumulate, the final track becomes clear. Several major survey projects supply these observations. Pan-STARRS in Hawaii uses wide-field cameras capable of capturing huge swaths of the sky each night, looking for faint moving points of light. NEOWISE, an orbiting infrared telescope, contributes from space by detecting heat rather than visible light, which makes it able to spot objects too dark to see from the ground. In addition, a network of international observatories reports their findings openly, so new candidates are confirmed or ruled out quickly. These combined tools mean that when something new emerges, its orbit can be nailed down within days or weeks. For the 7 inbound comets, the data now show none qualifies as a near-term impact risk. Each follows a safe trajectory that carries it close to the Sun, but not near Earth. Knowing this helps reduce public anxiety while still allowing researchers to gather valuable observations. The monitoring is not wasted effort, because every new orbit added to the catalogue helps refine our models of how small bodies move. Over decades, this has improved understanding of the solar system's structure and even its formation history. In plain terms, NASA issues alerts because greater awareness equals better science and better safety. Far from a warning to prepare for disaster, these alerts mean astronomers have unusual opportunities worth watching. With the big picture in mind, what seems at first like a cluster of risky arrivals is really another step in monitoring our dynamic neighborhood, before turning to the larger perspective of what they represent. The anatomy of a cometary time capsule. Far from being mere dirty snowballs, comets are complex, fragile structures that hold the key to understanding the primordial solar system. When we observe one of these 7 inbound visitors, we are looking at a 3-part machine: the nucleus, the coma, and the tail. To truly understand the scientific excitement around this cluster, we must look beyond their alarming-sounding paths and focus on what they are built from. The comet's nucleus is its solid core, typically a few kilometers across. This isn't a solid chunk of ice, but a highly porous matrix, more like a mixture of water ice, frozen CO2, methane, ammonia, and rock dust, all loosely packed together. Researchers debate whether it's an icy dirt ball or a dirty snowball, but the core takeaway is its extreme fragility. This porous structure gives the nucleus a surprisingly low density. It contains a large amount of empty space. This lack of structural integrity is why fragmentation is so common, especially as the comet is stressed by the Sun's gravity and heat. This nucleus material is special because it has remained chemically unchanged since the solar system's earliest days, preserved in a deep freeze far from the Sun's influence. Among the frozen gases, scientists have identified complex organic molecules, including things like simple sugars and amino acids. These are the fundamental chemical building blocks of life, prompting scientists to view the nucleus not just as a time capsule, but as a chemical factory. As a comet approaches the Sun, the solid nucleus transitions its material into gas, forming the second major structure, the coma. This is the fuzzy, extended atmosphere that envelops the nucleus, sometimes growing larger than the Sun itself, though incredibly tenuous. The coma forms as sunlight heats the nucleus, causing the ices to sublimate, or turn directly from solid to gas without becoming liquid first. The escaping gas violently carries with it fine dust particles, creating a cloud. Analyzing the coma is critical because it tells us the chemical fingerprint of the comet. Astronomers use a technique called spectroscopy to break down the light emitted by the coma. identifying the specific gases released, such as cyanogen, diatomic carbon, C2, and various complex hydrocarbons. These signatures allow researchers to compare the chemistry of different comets, like comparing a solar system-borne visitor to the interstellar comet 3I/ATLAS to see if they formed from the same universal materials. The third structure is the iconic tail, and it is often split into two distinct parts. The dust tail is the most visible, appearing broad, curved, and yellowish white. It's composed of microscopic dust particles pushed away from the nucleus by the pressure of sunlight itself. Because the comet moves along a curved path, and the pressure acts constantly, this tail sweeps back in a gentle curve. The second tail is the ion tail, or gas tail. This one is fainter, typically straight, and has a faint blue glow caused by carbon monoxide ions. It forms when the gases in the coma are ionized by the sun's ultraviolet radiation, and then are violently pushed away by the solar wind, a constant stream of charged particles flowing from the sun. Critically, the solar wind is so powerful that the ion tail points directly away from the sun, meaning it often precedes the comet on its way out of the solar system, giving it a counterintuitive appearance. Understanding this delicate machinery explains the value of missions designed to interact with these bodies directly. The most famous example is the Rosetta mission, launched by the European Space Agency, which reached Comet 67P/Churyumov-Gerasimenko in 2014. Rosetta didn't just observe the comet, it orbited it for 2 years and deployed the Philae lander to its surface. This mission was a scientific revolution. We learned that the nucleus wasn't a smooth sphere, but a rubber ducky shape formed by 2 different lobes that had gently fused. The most profound finding involved its water. Scientists were eager to confirm that comets delivered Earth's water, but by measuring the ratio of heavy water, deuterium to hydrogen, or D to H, in 67P, they found it was significantly different from Earth's ocean water. This single data point forced a major recalibration of the theory, suggesting that while comets contributed to Earth's water, they weren't the only source. Furthermore, Rosetta found complex organic molecules, including the simplest amino acid, glycine, confirming that comets could indeed deliver the fundamental precursors for biology. This direct observation provided data far beyond what any ground-based telescope could offer. Another mission that confirmed the fragility of comets was NASA's Deep Impact. In 2005, its primary goal was to intentionally crash a copper-tipped impactor into the nucleus of Comet Tempel 1. The experiment was designed to dig a crater and expose fresh, pristine material from beneath the comet's surface before it had been altered by solar heating. The result was a spectacular, massive plume of dust and ice, confirming the incredibly low density and high porosity of the nucleus, a fluffy, unstable structure. The data revealed fresh subsurface material, including silicates and water ice, that was largely untouched since the formation of the solar system. These missions, and the data they returned, inform how scientists are monitoring the current cluster of 7 comets. Every outburst of brightness, every fragmentation event, every chemical reading is compared against the Rosetta and Deep Impact findings to better categorize these time capsules. The scientific community is not merely hoping one survives its solar pass. They are eagerly anticipating the data that will be broadcast back to Earth, regardless of the comet's ultimate fate. The comet reservoirs, where they come from. The current gathering of 7 comets only makes sense when we look at their deep space origins. They aren't solitary wanderers, but members of vast icy populations held in deep freeze reservoirs at the edges of the solar system. There are two primary sources for comets, the Kuiper belt and the distant Oort cloud. The Kuiper belt is the nearer of the two, existing as a broad, donut-shaped region that begins just beyond the orbit of Neptune, extending out to about 50 times the Earth-Sun distance, 50 astronomical units, or AU. It is a massive graveyard of icy objects, which are referred to as Kuiper belt objects, KBOS. Larger KBOS include dwarf planets like Pluto and Eris. This region is the birthplace of short-period comets, such as Halley's Comet, which return to the inner solar system on predictable cycles of less than 200 years. Their orbits are relatively regular, a sign of their proximity to the orbital plane of the planets. They are dislodged from the Kuiper belt by the subtle, yet powerful, gravitational influence of the giant planets, particularly Neptune. Neptune acts as a cosmic shepherder, occasionally scattering a KBO inward, where it may become a short-period comet after a few close passes by the Sun. The second, and far more extensive source, is the Oort cloud. This is not a belt or a ring, but a massive, truly spherical shell of trillions of icy objects surrounding the entire solar system at distances stretching up to 100,000 astronomical units, a quarter of the way to the nearest star, Proxima Centauri. The Oort cloud is the source of long-period comets, which are the ones that take thousands or even millions of years to complete a single orbit and arrive randomly from any direction in the sky. It is this distant, massive sphere that likely produced the cluster of 7 inbound comets we are now tracking. The mechanism for dislodging these objects is not the gravity of a nearby planet, but the collective pull of the entire Milky Way galaxy, known as galactic tides. As the Sun and its Oort cloud slowly revolve around the galactic center, these tidal forces, combined with the occasional distant gravitational nudge from a passing star, gently stir the distant ice. This stirring can send an entire shower or cluster of comets, which were originally grouped together, tumbling inward toward the Sun over astronomical timescales. The simultaneous arrival of 7 comets is therefore highly irregular but entirely possible, potentially the result of a single, recent ripple through the Oort cloud. This vast system is also why the discovery of the Interstellar comet 3I/ATLAS is so important. While the 6 solar system comets formed from the same original nebula that created Earth, 3I/ATLAS was born around another star entirely. Its path is not bound to the Sun. It is merely passing through our neighborhood on its journey across the galaxy. The scientific value lies in the immediate and direct comparison we can make between our homegrown comets and a genuine galactic immigrant. The comparison is already underway with the first 2 confirmed interstellar visitors, Oumuamua and 2I/Borisov. Oumuamua, discovered in 2017, behaved strangely, accelerating without the visible tail of a comet, suggesting it might have been an elongated rock or an exotic form of icy body. 2I/Borisov, a year later, clearly acted like a comet, but its spectral analysis, its chemical fingerprint, showed it was one of the most pristine and chemically primitive comets ever seen, perhaps having never passed close to any star before. This evidence of exocomets, or comets from other star systems, confirms that the process of planet formation creates icy debris that is scattered across the galaxy. The simultaneous arrival of 3I/ATLAS with our own solar system comets is a chance to see whether distant planetary systems create bodies with the same ingredients we find near Earth, giving us an unprecedented multi-point laboratory to compare cosmic origins. The existence of these 2 great reservoirs, the nearer, relatively stable Kuiper belt and the vast ephemeral Oort cloud, helps explain why, even after billions of years, we continue to see these pristine bodies fall into the inner solar system. They are the leftovers of planetary formation, and their sustained presence means that, as old comets disintegrate or are thrown out of the system, new ones are constantly being replenished from the deep freeze of space. The clustering of the current 7 simply represents a temporary rush hour, a concentration of objects that were dislodged at roughly the same time. The fact that astronomers are tracking 6 Oort cloud objects alongside one interstellar object makes this event a rare calibration moment for our understanding of galactic dynamics and the flow of matter across the interstellar medium. It shows that our solar system is not isolated, but part of a dynamic, interconnected galaxy where matter frequently travels vast distances. Comets and the origins of life on Earth. The most compelling reason to study comets isn't the remote risk they pose, but the profound possibility that they may have helped make life on Earth possible. They are often theorized to be the delivery trucks that brought the essential ingredients, water and organic molecules, to our young, hot, and dry planet. This is a central question in planetary science: the role of small bodies in abiogenesis, the origin of life. For decades, comets were the prime candidate for delivering Earth's water, particularly during a turbulent period about 4 billion years ago, known as the Late Heavy Bombardment. During this era, Earth was pummeled by countless small bodies, potentially coating the planet in the water that formed our oceans. However, as missions like Rosetta have shown, this theory is now actively debated. The Rosetta mission measured the deuterium to hydrogen, DH ratio, in the water of Comet 67. P. Deuterium is an isotope of hydrogen, and the ratio of it to normal hydrogen acts as a stable fingerprint for water sources. Earth's ocean water has a specific DH ratio. Many comets studied, including 67P, have a significantly higher DH ratio, meaning their water is fundamentally different from ours. This suggests that while comets contributed some water, they were likely not the primary source of our vast oceans. This scientific finding has shifted focus toward asteroids, particularly the C-type carbonaceous asteroids that orbit closer to the Sun. Their water often exhibits a DH ratio much closer to Earth's, suggesting they were the more significant water carriers. However, the case for comets as essential building block providers is still strong when considering organic molecules. As noted earlier, missions have found glycine, a simple amino acid, and many complex hydrocarbons on comets. These are the bricks and mortar of DNA, RNA, and proteins. Even if comets didn't deliver all the water, they likely enriched the early Earth with the chemical raw materials necessary for life to emerge. This idea has led to the revival of aspects of the panspermia hypothesis, the concept that life's building blocks, or even dormant microbial life, could be transported between planets or star systems via these small bodies. Comets act as deep freeze storage containers, protecting these molecules from the harsh radiation of space until they impact a habitable world. The impact itself might have been a necessary step. Scientists have conducted laboratory experiments that simulate cometary impacts by firing gas guns at targets laced with simple organic molecules similar to those found on comets. These shock experiments have shown that the intense pressure and energy of an impact can cause a chemical transformation, converting simple molecules into more complex structures, such as peptides. Peptides are chains of amino acids and are the precursors to proteins. The high-energy shockwave, rather than destroying the molecules, might have provided the necessary energy to jumpstart the early biochemistry that led to life. Therefore, the early Earth may not have simply received the ingredients, but the violent act of a cometary impact provided the final kick needed to organize them into the first biological structures. The current cluster of 7 comets allows scientists to gather precise data on the exact mix of complex organic molecules these bodies carry. This real-time sampling of multiple comets is a unique opportunity to build a chemical inventory that will help future missions determine where to search for similar conditions that could lead to life elsewhere in our solar system, such as on icy moons like Europa or Enceladus, where cometary material may have penetrated the surface. Future monitoring and the next generation. The cluster of 7 comets serves as a clear indicator of the enormous amount of small body traffic still crossing the inner solar system, and it directly underscores the need for continuous, improved monitoring. The effort to track these objects is not slowing down. In fact, the next decade is poised to multiply the rate of discovery exponentially, moving us from tracking 7 comets to potentially hundreds. The most transformative new tool will be the Vera C Rubin Observatory, scheduled to begin full operation soon. Equipped with the largest digital camera ever built, its legacy survey of space and time, LSST, will photograph the entire visible night sky every few days. This unprecedented sky coverage and depth will allow astronomers to spot faint, distant comets and asteroids that current telescopes simply miss. If the current network can spot 7 comets in one go, the Rubin Observatory will likely find multiple times that number every single year, providing an ongoing, massive calibration set for planetary defense and cometary science. This flood of data will move the focus from finding objects to categorizing them. To handle this incoming data flood, NASA and international observatories are increasingly relying on machine learning and artificial intelligence (AI). AI algorithms are being trained to process the massive nightly images, identifying moving points of light faster and with greater certainty than human teams. Crucially, AI is also being deployed to improve orbital prediction. By crunching decades of data on objects and refining models of gravitational forces, including subtle effects like non-gravitational forces caused by cometary outgassing, AI can dramatically reduce the uncertainty cone for a new object's path within days. This is the real planetary defense, not preparing to shoot down a threat, but achieving orbital certainty years or decades in advance. The current 7 comets provide a perfect real-time test for these AI systems, allowing them to hone their prediction capabilities against a diverse set of objects. Beyond monitoring, the international community is planning ambitious new missions. While missions like Rosetta have provided incredible data, the future involves sample return missions. Imagine a spacecraft that could rendezvous with a comet, drill a core sample from its nucleus, and return it to Earth for detailed analysis in the world's most sophisticated laboratories. Such a mission could unlock definitive answers about the D/H ratio, the complex organic molecules, and the pristine, ancient composition of these bodies. The ultimate scientific legacy of the current cluster of 7 comets is that they provide a multi-point calibration event. By tracking 6 solar system objects of varying orbits alongside one interstellar immigrant, scientists can test all of their models, their AI systems, and their chemical theories simultaneously. This is more than just a momentary spectacle. It is a critical step in refining our predictive understanding of the solar system, ensuring that as our ability to monitor the dark corners of space increases, our knowledge of what waits there and what it represents increases alongside it. The scientific community is not issuing an alert of fear, but an alert of unique opportunity. Comets in human history and culture. Yet, to appreciate the current scientific perspective, the shift from alarm to opportunity, we must first understand the deep, primal fear comets have always invoked in humanity. For millennia, before telescopes and Newton's laws, a great comet was one of the most terrifying sights in the night sky. It appeared without warning, a fiery star with a sinister, vaporous tail, violating the perfect fixed order of the constellations. A comet was the ultimate harbinger of chaos. Across diverse cultures, they were almost universally viewed as omens, portents, and instruments of divine wrath. In ancient Babylon, they were seen as celestial writing, interpreted by priests to foretell the fate of kings. The Romans often associated them with the deaths of emperors or civil strife. The appearance of a great comet shortly after the assassination of Julius Caesar was seen as proof that his soul had ascended to the heavens, or perhaps proof that the gods were angry at Rome's tumult. This terror was not merely superstition, it was a visceral reaction to the unknown. Unlike the predictable sun, moon, and planets which followed regular comforting cycles, a comet was unpredictable. Its appearance coincided too often with significant destructive human events: plague, famine, war. One of the most famous historical linkages occurred in 1066. As Halley's comet blazed across the sky, it was interpreted by the English as a dreadful warning. When William the Conqueror successfully invaded and defeated the English at the Battle of Hastings, the comet was forever immortalized in the Bayeux Tapestry as the undeniable celestial precursor to the fall of the English crown. For centuries, this pattern held: comets were never benign. They were the celestial signatures of disaster, and humanity lacked the intellectual tools to strip them of their fearful power. The great shift began not with a comet, but with a Danish nobleman and astronomer named Tycho Brahe. In 1577, a brilliant comet appeared. At the time, conventional wisdom, based on Aristotle, held that comets were not celestial bodies, but meteorological phenomena, vapors that had somehow ignited high in the Earth's atmosphere. Brahe, using meticulous and advanced instruments from his island observatory, precisely measured the comet's position over many nights. He used the principle of parallax, the shift in an object's apparent position when viewed from two different locations, and discovered the comet showed no measurable parallax against the background stars. This meant the comet had to be far outside the Earth's atmosphere, orbiting among the planets. Brahe's discovery shattered the ancient belief in the perfection and fixity of the heavens and initiated the scientific deconstruction of cometary fear. The final triumph of reason came in the late 17th century with Edmund Halley. Having studied the work of his friend Isaac Newton and the newly formulated law of universal gravitation, Halley began to apply mathematics to the paths of historical comets. He noticed that the comets observed in 1531, 1607, and 1682 all followed nearly identical paths, separated by roughly the same interval of 75 years. In a magnificent intellectual leap, Halley proposed they were not three separate comets, but one single object orbiting the Sun on a massive, elongated path. He predicted its return in 1758. Halley died before seeing his prediction fulfilled, but when the comet reappeared exactly as calculated, it was named in his honor. It cemented the Newtonian view of the cosmos. Comets were no longer random, terrifying omens. They were predictable mechanical entities, governed by the same laws of physics that guided the tides and the motion of the planets. This single act of prediction transformed our relationship with the sky from one of superstition to one of scientific understanding. Yet, despite this scientific mastery, the cultural and psychological fear lingers. Even in the modern era, a bright comet can trigger media panic. When Comet Kohoutek arrived in 1973, it was heavily hyped as the Comet of the Century, set to be an unprecedented spectacle. When it underperformed expectations, it became a cultural joke, a source of media embarrassment. Yet it simultaneously generated intense apocalyptic fear among fringe groups, who saw its predicted failure as a sign of impending doom. More recently, films like Deep Impact and Don't Look Up demonstrate the modern obsession. The comet is now a metaphor for existential threat that humanity either can't handle or chooses to ignore. The cluster of 7 inbound comets we are tracking today exists at this nexus, the certainty of orbital mechanics clashing with the inherited dread of a celestial object with a glowing tail. The NASA alert is therefore a dual-purpose signal, a scientific call to observatories for data, and a necessary psychological countermeasure to manage public anxiety rooted in thousands of years of human history. Advanced planetary defense and asteroid mining. The current monitoring of the 7 inbound comets is a passive form of planetary defense. We are tracking them to confirm they pose no threat. However, this scientific vigilance is the foundation for the next, more active, stage of humanity's relationship with space, intervening to protect our planet. The field of planetary defense is not theoretical science fiction. It is a serious, internationally coordinated engineering challenge focused on diverting a potential impactor, usually a near-Earth asteroid, long before it poses a danger. When considering the possibility of a threatening object, engineers must have several diversion methods prepared. The first and most straightforward is the kinetic impactor. This method, exemplified by NASA's DART mission, Double Asteroid Redirection Test, involves sending a high-speed projectile, essentially a heavy spacecraft acting as a bullet, to slam into the threatening object. The kinetic energy of the impact transfers momentum, causing a small, measurable change in the object's velocity. The key is to apply this subtle nudge years or decades before the potential impact, allowing the small velocity change to translate into a large enough change in position to miss Earth entirely. The DART mission demonstrated this concept by successfully changing the orbit of the asteroid Dimorphos, validating our ability to execute this precise maneuver. The second method is the gravity tractor. This is arguably the most elegant and low-risk diversion technique. It involves flying a heavy spacecraft in formation close to the threatening object without actually touching it. The spacecraft's own minuscule gravitational pull is enough to slowly tug the object off course. Because the method does not involve a collision or contact, there is no risk of the object breaking up into multiple pieces, which could create multiple impact hazards. It's a slow, gentle, and highly predictable process, making it the preferred method for objects where a long lead time is available. The third method is the extreme measure, the nuclear option. While this is often the most common plot device in movies, it is the most controversial and least desirable engineering choice. Using a nuclear blast to divert or vaporize an object carries 2 major risks. First, it violates the Outer Space Treaty by deploying nuclear weapons in space. And second, depending on the detonation location, it could fragment the object. While the blast might vaporize the core mass, the resulting shower of smaller, highly radioactive pieces would be a much wider and more complex threat to track and predict than the original object. Therefore, it is strictly considered an absolute last resort for objects discovered too late for a gentler push. Finally, there is the emerging concept of ablation or focused energy, where high-powered lasers or focused solar energy are used to vaporize material off one side of the object. This rapid vaporization creates a tiny, sustained thrust, gently pushing the object off course, a high-tech version of the natural process of outgassing that creates a comet's tail. The same small bodies we monitor for defense are also now viewed as the key to unlocking the future of space exploration. As vast repositories of resources, comets and asteroids are not just rocks. They are the low-hanging fruit of the space economy. The focus is primarily on two critical resource types: water and metals. The water stored in comets and icy asteroids is the most valuable commodity in space. Once retrieved, this water, H2O, can be used for life support for colonies, but more importantly, it can be split via electrolysis into its constituent elements: hydrogen, H2, and oxygen, O2. These are the components of high-performance rocket fuel. The ability to refuel spacecraft in space at an orbital gas station using asteroid-derived water would dramatically reduce the cost and technical challenge of deep space missions. No longer would an entire mission's fuel supply need to be lifted from Earth's deep gravity well. The second class of resources is metals. Many near-Earth asteroids are believed to be the cause of ancient shattered protoplanets and are rich in valuable metals. Iron and nickel are crucial for construction, but the true wealth lies in the platinum group metals, PGMs, which include platinum, palladium, and rhodium. These metals are rare on Earth but are essential for modern technology: catalytic converters, electronics. An individual, metal-rich asteroid could contain more platinum group metals than have been mined on Earth throughout history, leading to the term trillion-dollar asteroid. This potential for resource exploitation drives the emerging field of asteroid mining. This economic push has triggered a necessary but complex debate over space law. The 1967 Outer Space Treaty states that no nation can claim celestial bodies. However, several nations have passed domestic laws granting their citizens the right to own resources they extract from space. This ambiguity sets the stage for a new, complex economic and legal frontier, one where the comets and asteroids we currently monitor for defense become the foundation of a space-based economy. The deep future and interstellar probes. Ultimately, the study of comets forces a philosophical shift, looking not just at the immediate future of Earth, but at humanity's place in the universe. Comets are the only physical objects we have studied that directly link the formation of our solar system to the vastness of the interstellar medium. This deep time connection opens the question of cometary habitability. If comets are rich in water and organic molecules, and if geological or gravitational forces could create liquid pockets beneath their frozen surfaces, perhaps warmed by the radioactive decay of internal materials, could these small, icy bodies briefly harbor life? While speculative, this warm comet hypothesis has a direct analogue in our solar system: the icy moons of Jupiter and Saturn, particularly Europa and Enceladus. Europa and Enceladus are essentially massive, extremely active comets. Beneath their thick, icy shells, tidal forces from their giant host planets generate immense heat, maintaining vast global subsurface oceans of liquid water. These oceans are now considered the most promising places in the solar system to find extant alien life. The same materials we find in a cometary nucleus, water, salts, and organic compounds, are being mixed with hydrothermal vents on the seafloors of these moons. Understanding the delivery and composition of the current 7 comets and the interstellar visitor among them helps refine our understanding of the chemical starting points for life on these distant, icy worlds. We are preparing to send missions like the Europa Clipper to further explore this possibility, recognizing that the principles of cometary science apply directly to the most profound question in astrobiology. This deep future view extends beyond our solar system entirely. Comets, traveling immense distances in their orbits, represent the first, most massive barrier to true interstellar travel. The Oort cloud is so vast that any spacecraft traveling to the nearest star, Alpha Centauri, must first pass through this immense sphere of trillions of icy, the deep future, and interstellar probes. Continued. Star system must first pass through this immense sphere of trillions of icy bodies. While the objects are sparse, their collective volume represents a navigation and collision challenge. This challenge gives context to ambitious long-term concepts like Project Starshot, an initiative aiming to send tiny, light-sail-propelled probes to another star system. Before such a project could succeed, a thorough mapping and understanding of our own Oort cloud, which we gain by studying the comets that fall inward from it, is absolutely essential. Comets are therefore not just remnants of the past, they are interstellar stepping stones. When the interstellar object 3I/ATLAS passed through, it gave us a precious, fleeting sample of a neighbor star's material, proving that matter is exchanged across the galaxy. This is the ultimate horizon, the realization that the components of our solar system, and by extension, the building blocks of life itself, are not unique to Earth, but are the common denominator of galactic formation. Our existence, rooted in the geology and chemistry of our planet, is chemically connected to the far reaches of the Oort cloud and the depths of interstellar space. Final summary and call to action. The arrival of these 7 comets, viewed through the lens of human history, modern engineering, and cosmic ambition, represents far more than a momentary spectacle. It began as a fleeting alarm, rooted in millennia of fear and superstition, but through the rigorous application of science, that fear has been wholly transformed into informed vigilance and unprecedented opportunity. We have shifted from viewing these bodies as omens of destruction to recognizing them as the keys to our past and our future. They are the pristine samples of our cosmic birth, providing the chemical recipes of a 4.6 billion-year-old nebula. They are the essential building blocks of life, holding the water and organic molecules that may have seeded the early Earth. And critically, they are the proving grounds for our future as a spacefaring civilization. The work of the Planetary Defense Coordination Office is not about panic. It is about precision. It is the realization that the greatest defense against any cosmic hazard, be it a fragile comet or a rocky asteroid, is not a missile, but math. By using sophisticated telescopes and AI algorithms, we can refine orbits and predictions, ensuring that what might once have been a terrifying, unpredictable event is now a scheduled, monitored observation. The exponential increase in discovery promised by future surveys like the Vera C. Rubin Observatory means that the era of surprise celestial visits is drawing to a close. We are entering an age where the solar system's inventory will be known, charted, and understood. Therefore, the legacy of this cluster of 7 is a call to action for all of humanity. It is a reminder that we live in a dynamic, sometimes violent, but endlessly fascinating cosmic neighborhood. The true danger is not the comet, but ignorance. By supporting the research, the missions, and the educational outreach that flows from these discoveries, we are investing in the scientific literacy required to navigate the cosmos safely and intelligently. We are preparing the groundwork for the next generation of explorers who will not only travel to these icy reservoirs, but may use their water and minerals to fuel humanity's permanent expansion into space. The time capsules of our past hold the rocket fuel for our future. The 7 visitors remind us that the sky is not a distant static backdrop, but an enormous, shared laboratory, one that promises discoveries far greater than the fear they once inspired. And the most compelling question remains: if our improved monitoring system can find these 7 today, what incredible new insights and even greater possibilities will we uncover tomorrow? The existential messenger, comets and deep time. The shift in perspective from fear to fascination is, at its core, a confrontation with deep time, the vast, nearly incomprehensible age of the universe. The comets we track today are not simply 7 objects. They are the physical embodiment of epochs. The 6 solar system comets began their journey billions of years ago, before Earth's oceans formed, existing for an unimaginable duration in the deep freeze vault of the Oort cloud. The single interstellar comet, 3I/ATLAS, represents an even greater span, having spent perhaps billions of years navigating the void between galaxies, originating from a star system that may have died out long ago. When a comet sublimates near the Sun, it releases material that is chronologically ancient but chemically pristine. We are, in effect, touching a time before time, holding a tangible connection to the cosmic infancy that preceded our own history. This realization lends a profound urgency to our monitoring efforts. Every observation we make is a fleeting conversation with the deep past, a chance to glean knowledge before the sun's heat fragments the messenger and scatters its evidence forever. This is why the fragmentation of a comet, while less spectacular than its survival, is scientifically just as valuable. It reveals the internal structure and pristine materials that have been locked away for eons. This understanding of deep time also recontextualizes our place in the universe. Comets demonstrate that the materials required for life, water, complex organic molecules, and the necessary energy for their fusion, are not an improbable miracle unique to Earth, but a cosmic certainty. They prove that the building blocks are everywhere, carried as seeds across the interstellar void. This truth underpins the entire field of astrobiology and validates the enormous resources we dedicate to missions like the Europa Clipper. If the basic chemical principles observed in a fragile, incoming comet are replicated in the vast subsurface oceans of an icy moon, the statistical probability of life elsewhere in the cosmos rises exponentially. The comet is not merely delivering a chemical sample, it is delivering an existential proof of concept. The ultimate lesson of the 7 comets, therefore, is not about the risk of impact, but the certainty of connection. We are made of the same stardust as these objects, driven by the same gravitational and thermal forces that dictate their paths. By tracking these icy messengers, we are not just guarding our planet, we are reading the history of our galaxy, charting the potential pathways for life, and preparing the foundation, the scientific knowledge, the engineering skills, and the necessary ethical framework for humanity's inevitable expansion into the cosmos. Conclusion: the enduring legacy of the Seven. The 7 inbound comets remind us how fragile and plentiful these icy remnants are. Each one is a leftover from the early solar system, yet many will not survive their passage near the Sun. The consensus view is that their arrivals are not unusual, but clustering makes them more noticeable. What may sound like a warning is actually a natural cycle, steadily showing us how planets and smaller bodies first took shape. If so many comets only became detectable with recent surveys, a valid question is what the next decade of improved monitoring might uncover waiting in the dark. The final legacy of these 7 visitors is the enduring strength of human curiosity over human fear. They have served as catalysts for historical breakthroughs, as engineering challenges for planetary defense, and as philosophical anchors to the concept of deep time. From being terrifying omens to being potential refueling stations for future starships, the comet's role has come full circle. The scientific alert is now finished, the data is collected, and the objects will soon swing back into the silent, frozen depths of space. But the knowledge they leave behind, of our origins, our resources, and our place in a vast interconnected galaxy, will continue to propel our civilization forward long after these 7 icy messengers have faded from our view. Conclusion: 7 inbound comets remind us how fragile and plentiful these icy remnants are. Each one is a leftover from the early solar system, yet many will not survive their passage near the Sun. The consensus view is that their arrivals are not unusual, but clustering makes them more noticeable. What may sound like a warning is actually a natural cycle, steadily showing us how planets and smaller bodies first took shape. If so many comets only became detectable with recent surveys, a valid question is what the next decade of improved monitoring might uncover waiting in the dark.